Right. Yes, okay. So if we had, say, methyl bromide, for example, and we threw in our magnesium, the, the, the common sort of way that this is envisioned of working is that the actual formation of a Grignard reaction involves radicals. So one way you could think about it is doing it like, oops, what am I doing here? Is something like this. Make that thicker here. And so that's one of the ways that this is envisioned of working. Some of the evidence for this is that when you've got when you're making so the very thing which you used, Mg, one of the byproducts in this reaction is biphenyl. And so this is what is called Wirtz coupling. And this happens if the concentration of the ether is too high. And so they believe that this happens because two of the phenyl radicals get together and react. So that's if the concentration of the ether is too high, like you don't have enough of it, so they're all in close proximity. So this is what's commonly sort of thought of as how this works. I don't know if it's definitively been concluded as to be that, but for what we're involved with, if you are curious as to how that happens, that's basically how we'll describe it. So the end of last class, we I think we were describing essentially the various types of Grignard reactions that could take place. So the second one I'll just highlight here is that if we've got, I'll do two things actually. No, let's erase this. A question that is very commonly asked, if you look at organic chemistry textbooks and that sort of thing, is Grignards plus esters. So the interesting thing about esters is that the Grignard can be added twice to an ester. Just like when we're doing a reduction with lithium aluminum hydride, it can be, that was added twice, same sort of thing here. And textbooks love to use cyclic esters. So these are called lactones. And I'll basically describe why in a second. So let's pretend that we are adding excess methyl magnesium bromide. And this is an ether. So the product we're going to make is going to look like this. Oh yeah, and then that will be step one. The second step will be our acid. We'll do the mechanism in a second here. I'm just counting carbons here. So the methyls, these two methyls here are here and here. And the H3O plus protons, this guy, they're going to be here and here. So let's do the mechanism. So the reason why cyclic lactones are like cyclic esters or lactones are so common is because the two halves of it's connected to itself. So there's you're not losing part of your product. So let's do the mechanism. So these electrons attack here. This is delta minus, this is delta plus, delta minus. And we're going to break the pi bond. So the pi electrons move up onto the oxygen. Next step, this tetrahedral intermediate is going to break down, and this is going to generate a ketone plus the phenolic sort of anion here, the phenolate, I guess. Call that. So let's number this A and B, A and B, A and B. So now we've got a C because we've added that methyl group. Now this technically could be an equilibrium. So we could have this negative charge attack the ketone and go back to where we started from. But in the presence of excess magnesium, Grignard, the next step is going to happen quite quickly. Okay, so we'll draw this in green. Okay, so these electrons come here. So remember, carbon's the delta minus, carbonyl's the delta plus, delta minus. Then these electrons will move there, and our product will look like this. So let's number this again, A and B. So our second methyl group has now been added, and it'll stay in this form until we add our acid to it. So this would be the second step. I'll draw this in orange. And once acid's thrown in there, the negative charge is going to grab the protons. And that will give us our final product. So the key point is that we've added 2 methyl groups to the starting carbonyl. So carbon B at the start now has got 2 methyl groups on it. A and B. Now, if we do a Grignard reaction with a regular ester, for example, we'll just do an example right here. Just some regular ester. And let's say we add excess methyl magnesium bromide. One, 2, H3O plus. The reason why using lactones is so, it's used a lot for textbooks and stuff, is that, okay, let's number our carbons. A, B, C, D. So carbon D is going to get 2 methyl groups. It's going to get 2 of whatever the Grignard is. So in this case, it's a methyl. So our product will be A, B, C, D. Methyl, methyl. You'll notice that the rest of the molecule here, this OMe, it's no longer there, it's gone. But in the case of this lactone at the start, where if we were to, that oxygen is still a part of the product. So let's draw it like, oh, it's right over here, right? So it's still part of the product. So that's why lactones are used a lot, because you can sort of gauge if everyone's got the, understands where those nucleophiles attack. Which, are they close to the carbonyl oxygen, or are they the pi bonded oxygen or the sigma bonded oxygen? So it's a way of basically testing that. So lactones are used often in questions for that type of thing. Yeah, so Grignard reagents, they add to the carbonyl. If you start with an aldehyde, you'll get a secondary alcohol. If you start with a ketone, you'll get a tertiary alcohol. If you start with an ester, you'll get a tertiary alcohol, but 2 of the groups will be the same. So yeah, the summary is basically this. So secondary. So this is now tertiary, and esters excess. Tertiary. That the key point here is that this R is there twice. Now, I guess the last thing, okay, so let's do one more question here. One more. Let's say that you had, okay, before I do that, any questions? All right, that's a good sign. Okay, it's either a good sign or a bad sign. The next question is, okay, let's do one more example. Let's pretend that we have got this, and we are adding phenyl. Let's make it. Let's use the one that you guys made. Okay, so we're trying to be green chemists. We're using one equivalent of our methyl magnesium, phenyl magnesium bromide. First step, second step, we're adding in our acid. What is our product? Everybody take 30 seconds and draw out what our product is. If you've got something, let me know. Okay, it's time for the big reveal here. So what is the product that we made? The product that we made will be as follows. So you add your phenyl magnesium bromide and ether, stir it for a little while. At the end of the reaction, you throw in your acid. Then you do your acid bit, your liquid extraction to get your products. And when everything is said and done, what you end up making is this. You end up with your starting material and benzene. So what has happened?
Did that acidic proton interfere with the reaction?
That's right. So the thing to remember is with Grignard reagents is that they're not only very excellent, massively good nucleophiles, but they are super basic. So they will grab protons faster than anything. So if you had only one equivalent of your Grignard reagent, this is going to come grab this proton, and then you will form the conjugate base. And it's going to hang out like this until the second step, where you add your H plus, and then that would form, and then you would get your product. So there's a way of getting around this, and that is to use excess Grignard reagent. So you would, if you used excess, the first equivalent would deprotonate that acidic proton, the second equivalent would attack the carbonyl. So that's one way to solve that issue. It becomes a bit more tricky if, let's say that you wanted to make if you wanted to make a Grignard reagent like this, and you essentially, so if you started with so species like this, and you wanted to put in like magnesium and ether to make that and use this as in your reaction. The trouble is you can't do that because there's an acidic proton on there. So chemists have come up with a way of dealing with this. And so that's what we'll talk about. So there is a way of circumventing this problem, and basically all second-year textbooks use this stage of the game to discuss what is called, what will be known as a protecting group. So all of our, so at the start of Organic 1, we had a whole bunch of different functional groups. We sort of used them as our alphabet, and different functional groups have got different chemical reactivities. And some of them will interfere in the chemistry of, because they're too reactive. So what a protecting group is something that can be easily installed and easily removed. And it is going to block the reactivity of that functional group. And so the purpose is basically to block any reaction on that functional group. So aldehydes have protecting groups, ketones have protecting groups, esters, not so much. I guess there's a couple of them. Alcohols have protecting groups. Thiols will have protecting groups. Any group which is reactive, there's a way of transforming it into something which is non-reactive and then transforming it back to what it originally was. So when I say that that a protecting group is easily installed and easily removed, we are in the process, we are going to conserve that functional group for what we want to use it for. So in the case of alcohols, so ROH. So this chapter is on alcohols. So remember, they are both Lewis acids and Lewis bases, depending upon what they react with. And it's the acidic proton that is often which causes a lot of the reactivity. If you think of something which is very similar to an alcohol, the ROR, so ethers, these tend to be not particularly reactive. So we use two of them very commonly in as solvents, right? So remember, THF. Remember the aprotic solvent. And the solvent that we were using with the Grignard reagents, which was diethyl ether. So I call this the Batman molecule because it looks like a bat and it looks like one of the little things Batman would throw. So, so this is diethyl ether. And so these are common solvents that we use with very reactive molecules, and they don't react at all, right? So we could conceivably use an ether as a protecting group, but the trouble is it's hard. It's to convert an ether back to an alcohol, which we're going to do in the next section. It's hard. So you have to use really strong conditions. So an actual ether itself isn't particularly useful, but there is a version of it that is easy to install and easy to remove. And this is, and what we're going to use here is Si. So on the periodic table, carbon, right beneath it is silicon. So we are going to make the silicon equivalent of an ether. And so we call these guys silyl ethers. So a silyl ether looks like this. RO Si. And I'll just put 3 lines on it because silicon, like carbon, is bonded to 4 different things. Now, some things to silicon, it's lower on the periodic table. So when it bonds to things like carbons and oxygens, its bond length slightly longer. But silicon does have an affinity for both oxygen and fluorine, and that's going to be the key part here. So how do we make a silyl ether? Well, this is really, it's not hard at all. So you take your alcohol, and you react it with a silyl chloride. And you need a base here to remove a proton at some stage. So we use triethylamine, and it's often done in dichloromethane. So this will look very similar to a reaction which we've seen before when we're making a good leaving group, when we had like triethylamine, dichloromethane, and say a sulfonyl chloride. The mechanism is slightly different, but the reagents are all very similar. So in this case here, we would make what were we making here? We were making the mesylate. But in this case here, we'll be making the silyl ether. The other byproduct will be the nitrogen, the triethylamine, which will be protonated. Will be a chloride floating around, forming a salt. And there we go. Technically, this isn't, in the case of the reaction with the silyl chloride, this is technically an SN2 reaction. And you'll say, wait a second, Dr. Hill, last term, this couldn't happen on a tertiary carbon, right? But the silicon-carbon bond is so much longer that it's not sterically hindered. So it's basically an SN2 type reaction. Now to remove like the first part, and the yields for these things are like 95 to 100%. So it's really, 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 really easy to put on. And there's a whole bunch of different silyl chlorides that you could use. I've used the simplest one with 3 methyl groups, but chemists have developed all sorts of them with like, say, 3 phenyl groups, they've even got one with 2 tert-butyl groups on it. And it all depends upon, there's a couple with regard to their stability and how you take them off. Like you could do a whole section of a course just on silicon protecting groups. But anyway, but they're really easy the yields are essentially 100% to put on. So that's the first thing, which is good. You need a high yield to put it on, but you also need a high yield to take it off. And one of the most common ways to do this is with fluorine, which was what, sorry, I should say fluoride. So this is a ammonium salt. So nitrogen with 4 butyl groups. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Nitrogen's got a positive charge. With these 4, remember salts aren't particularly soluble in nonpolar solvents. THF is polar, but with these larger chains, that helps with the solubility of it. And then fluoride is basically by itself as an anion. And the way that this works is that this just comes along and attacks the silicon. Oops, it's not very good. It's thought to form a pentavalent silicon because silicon can have a expanded octet because it's in the next row. But for what we're thinking of, just think of it as a reaction like this. And then this THF is not dry. It's got water in it. And so you form your alkoxide, which then gets protonated by H+. Now you might say, oh, wait a second, didn't we in organic 1 just do a whole section on what's more stable, F- versus O-? And F- is stabilized by electronegativity. So why would this reaction take place since we're making an O-? The thing which we're missing in that whole formula is that the silicon fluorine bond is so incredibly strong that it's a thermodynamic sink. So it overcomes this energy difference for the oxygen going up because the oxygen later gets protonated anyway. So it's the reason why this works so well is that this fluorine and the silicon have got this natural affinity for one another. And so it attacks that silicon, and that's how we get it. So this basic 2-step, I guess I should give you the acronym. This salt here has got a name called TBAF for tetrabutyl ammonium fluoride. So TBAF. And there's T-bi and like T-bi would be tetrabutyl ammonium iodide. That's another one which is made. But it's a very common source of F minus that you can buy. They sell it in a bottle in a solution in THF. And it's just so easy to use. You just put them in your reaction and boom, it goes. So it's this process of so the yields for this second step are often approximately 95 to 100% as well. So it works really, really well. So if you wanted to do a Grignard, which this is the whole point of this exercise. So let's say we had our first step would be, oh, right. And the acronym for this guy here is TMSCL. So many acronyms. Trimethylsilyl chloride. The problem with this one, with TMSCL, there is, when you guys did a little workshop with infrared and NMR in first term, right? I think you did. And there was something called TMS in that, which was tetramethyl silane. And so that's just silicon with 4 methyl groups on it. Tetramethylsilane. And that was used as an internal standard in NMRs. You probably, I don't know if you remember that or not, but so, yeah, just pay attention if there's a chlorine or a bromine or what have you attached to it. So that's the acronym. So anyway, so the first step we would react this with our triethylamine, dichloromethane, and this would give us our next step would be the magnesium in ether. This would form our reagent, so silicon. Since there's no acidic proton there anymore, it doesn't react, doesn't interfere. Then we're going to add it to some carbonyl compound. Let's add it to, I don't know, cyclohexanone, THF. And we'll do an acidic workup, add a little bit of H3O plus in there. Well, let's do it the other way. Let's count the carbons here. So 1, 2, 3, 4. And so these electrons are going to attack here. Those electrons are going to move up. The oxygen is going to get protonated with that hydrogen. So we will have and we need 4 carbons. 1, 2, 3, 4. 1, 2, 3, 4. And on carbon 4, we're bonded to the silyl group, silyl ether. And then the last step would be that we would react this with our fluoride. And our final product would look like this. So that would be the equivalent of essentially using it's the equivalent of using this type of reagent because you've got the appropriate number of carbons. 1, 2, 3, 4. But remember, we can't make what I've got in quotes here. You can't make it, but it's equivalent of doing that. So yeah, so most textbooks bring up the oxygen protecting group here. The alcohol protecting group here, because you make something which is easy to put on and easy to put off, take off, and the yields are high. So it's a neat little way of doing things. So we've learned our first protecting group, which is a silyl ether. So that's good. I've used triethylamine here as the base when we're adding the silyl, when we're making the silyl ether. Any nitrogen based non-nucleophilic, or any basically like you use triethylamine, you could use basically any tertiary amine, or this guy here, which is pyridine. Those are all useful bases you can use, but triethylamine is the most common one. Okay, so so we can make alcohols from carbonyl compounds from reducing them, or by using Grignard reagents. And I guess the one thing, just a reminder, is that sodium borohydride plus an ester, there's basically no reaction. It's not a strong enough reducing agent. You can find the odd occasion where it does work, but the majority of the time it doesn't. So just keep that in mind. So if you want to reduce an ester, you need to use the lithium aluminum hydride. Oh, lithium. Just keep that in mind. Now, so, right. So this is the reduction side. The other side was the oxidation. So we've essentially covered the reductions. We've taken carbonyl compounds, we've reduced them, and we've made alcohols. The thing we need to do next is the opposite. Take an alcohol and oxidize it. to the various carbonyl groups. So that's what we'll do next, unless there's any questions. Okay. Okay, so let's take a couple of let's take a primary alcohol. Let's take a secondary alcohol. And let's take a tertiary alcohol. And so let's do an oxidation reaction. So this would be an aldehyde. Oxidation. This would be a ketone. So in an oxidation reaction, the carbon's losing a hydrogen and the oxygen's losing a hydrogen, at least for these first two. The aldehyde can actually be further oxidized to the carboxylic acid. So we can actually add another the ketone, of course, can't be because it already has 1, 2, 3, 4 bonds. So a ketone can't be oxidized anymore. Tertiary alcohols, likewise, there is no oxidation of a tertiary alcohol because if we draw this, the problem is we've got too many bonds to carbon, right? We've got 1, 2, 3, 4, 5. So that's a big no-no. So tertiary alcohols are effectively immune to oxidation. And so out of all of these, probably the most interesting one is the primary alcohol because it can be oxidized into two different products, whereas the ketone is, the secondary alcohol can only be oxidized to the ketone. So we'll first we'll just discuss some oxidizing agents. Okay, so most of the oxidizing agents that are discussed in, like we could do a month-long course just on oxidizing agents. It would be dreadfully boring, but there's hundreds of oxidizing agents out there to do a whole myriad of different things. But the ones that are talked about the most in second-year textbooks are chromium-based oxidizing agents. So they use chrome. So either chromium trioxide or something like this dichromate. And if either of these are basically put in acid and water, they end up making chromic acid, which looks like this. And it's a very powerful oxidizing agent. So the reagents that are used usually start off with CrO3 or Na2Cr2O7, something like this. But the two generic names of the oxidizing agents are Jones reagent, Jones, or PCC. Sounds like a. So Jones reagent is either you make it by either adding Na2Cr2O7 plus H2SO4 in water and acetone, or they make it from CrO3 with sulfuric acid, water, and acetone. So Jones reagent is basically a cocktail of these reagents. So what I'll often do is just write Jones. Pyridinium, PCC, this stands for pyridinium chlorochromate. And so this is, it's basically CrO3 with pyridine and chloride. So yeah, pyridinium chlorochromate. Pyridinium chlorochromate. And the two of we'll talk about why. So I'll just call it PCC. Now, did anyone see the Aaron Brockovich movie? It was out in the 60s, and in the early, I think it was out in the 90s. Julia Roberts. I'll take that as a no. You should watch it. It's a fascinating movie. But anyway, part of the story is about chromium poisoning of the population in, I think it was Southern California. So chromium isn't particularly something, it's not good for you. So, but it is a powerful oxidizing reagent. And the interesting thing about it is that when you've got, it's orange, right? So your solution of your Jones reagent in acetone and water is orange. And then as the reaction takes place, it turns blue. So this is often used as a test for alcohols. You can just add an alcohol to your Jones reagent, and if it turns blue, oxidation's taken place, and you got, so it was used a lot in the past, but chromium's not good for you. So, but let's do. Oh, the class is basically over. So what we'll do at the start of next class is we will do the mechanism of how this oxidation works. But yeah, so, and what we're going to see is that one of them is able to stop the reaction at the aldehyde, whereas the other one is going to go all the way to the carboxylic acid. And I see that there's a. Okay, so what we'll do is we'll pick up on the mechanism of this at the start of next class. All right, have a good weekend. What I plan to try to do this weekend is have post a short, tiny assignment on synthesis type stuff, like reaction roadmaps and that sort of stuff. I hope to have it up by Sunday. It won't be particularly long, just to, because we did that right after the first midterm, just to remind everybody about that. Okay. All right. I hope everyone is has a good weekend and a good remaining part of Thursday. And I will see everybody on Tuesday.
Thank you.
You bet.